Hi, my name is Tom and I'm a mechatronics student at the University of Newcastle. In this video, I will be presenting my work on bipedal locomotion for the NUBOTS Robotics Research Group. So let's dive right in.
NUBOTS consists of a number of students and academics from the University of Newcastle, which compete in RoboCup, which is a robotics competition where universities from around the globe compete. The goal of RoboCup is by the year 2050 to develop a fully autonomous humanoid robot team which can compete and beat a professional soccer team. Taking a step back, why do we actually need bipedal locomotion? Well, a big argument is made that the majority of the world we live in is designed for humans, so that if we want robots to be able to navigate this world, the most ideal robots are bipeds or humanoids. There are many potential applications for humanoids in things such as aged care, delivery services, and disaster response. The NUBOTS team uses the NUgus hardware platform, which is a modification of the IGOS open hardware platform originally developed by Bonn University. In order to develop a mathematical model of the NUGUS platform, a forward kinematic model was used. A forward kinematic model is a commonly used method used to represent robotic manipulators and consists of joints and links interconnected in a tree. A forward kinematic model can be mathematically represented as a product of homogeneous transformations between each of the joint frames. The NUGUS platform is around 90 centimeters tall and consists of 20 joints and 20 individual links. This diagram represents the forward kinematic model of the NUGUS platform and highlights the direction of rotation of each individual joint relative to the base joint frame. To obtain highly accurate model parameters, such as the length of links, the center of masses, and moments of inertias, I created a one-to-one assembly of the NUGUS platform in the CAD software Onshape. Within Onshape, you can also specify the locations of all of the joints within the robot. By specifying the locations of the revolute joints in the Onshape model, you can utilize an API developed by Team Roban, which automatically generates a UIDF file. A UIDF file is a universal robot description format, and it's commonly used in a number of robotic simulation environments. The UIDF file automatically generated will include highly accurate kinematic parameters such as link lengths and will automatically include the inertia parameters rotated into the correct joint frames. So how can we get a robot to walk and not fall over? I would like to propose a method which first involves step planning, which generates foot positions based on gait parameters such as the step length, height, and time. With these foot positions, we'll then use gait generation, which will generate motion trajectories for the robot to follow, while also ensuring some stability criterion are met. Now with the generated joint angles, we will use actuation and some low-level controller of each individual servo motor to achieve these target positions. Let's have a look at the first stage, step planning. This involves taking some gait parameters, step length in the x direction and the step length in the y direction, and the number of footsteps, and generating a matrix where each row of the matrix represents a different target foot position. This can be more clearly understood by observing the following animation. Here we can observe the footstep generation process for some gait parameters of 0.3 meters in the x direction and 0 in the y direction. Now that we have a step plan, let's now look at the gait generation stage. The first step after generating target footstep positions is to generate trajectories for the swing foot to follow to reach that target swing foot position. This can be achieved using polynomial splines. Splines are generated by interpolating between specified waypoints, and in this case, the waypoints are specified via the gait parameters and the current footstep positions and the next footstep positions, as shown here on the right. A crucial component of the gate generation stage is ensuring some stability criterion are met. The first method for this I will discuss is known as the quasi-static method. This control architecture ensures that the projection of the center of mass always remains inside the support polygon created by the feet which are in contact with the ground. With this approach, only slow walking speeds can be achieved, as we assume the robot is statically stable. This means that at any moment throughout the gait cycle, if the robot was to stop, the robot would remain stationary. To implement this method, we must first look at inverse kinematics. Inverse kinematics takes in a desired trajectory for the swing foot and solves the required joint angles needed to achieve that trajectory. Now this can be solved using numerical optimization. Now this is quite useful as we can embed the quasi-static nonlinear constraints directly in the optimizer, which is solving the inverse kinematics problem. Shown here is the cost function which was used to solve the inverse kinematics problem, coupled with the nonlinear quasi-static constraints, which ensure that the center of mass relative to the support foot planted on the ground remain within the support polygon. Shown here in the following plot is the center of mass position relative to the support foot during a single step. To better observe the gait achieved using the quasi-static method, a visualization was created to show the kinematic configuration of the robot during the gait cycle. To further validate the gait cycle achieved, a physics simulator can be used. Additionally, due to the travel restrictions imposed by COVID-19, the 2021 RoboCup competition was converted into a solely virtual competition. This required the league to decide upon a physics simulator for the RoboCup competition games to run on, and the chosen simulator is known as NUBOTS, developed by Cyberbotics. This required the NUBOTS team to develop a WeBots robot model which aimed to accurately resemble the real-life hardware of the NUGUS open platform. Each server of the NUGUS in the WeBots model were accurately modeled using real-life parameters sourced from the respective datasheets. These included torque constraints, velocity constraints, damping, and static friction. We even went to the length of attempting to model backlash in the servos. However, the WeBot simulator was unable to accurately model the effects of this. As observed, the quasi-static method was able to achieve a stable walk within simulation. Looking at it from a front-on view, you can observe the torso of the robot tilting over the top of a support foot during a single step. With some manual tuning, we were able to increase the speed of the quasi-static method considerably. To further validate that the quasi-static method was working, WeBots provides a visualization tool to observe the center of mass location projected onto the support polygons. The direction of the walking motion is also not constrained to only walking forwards. Using the step planner shown earlier, we were able to achieve backwards walking motions, strafing, and diagonal walking. I will now discuss another method investigated to ensure that the robot is stable during the walking cycle, known as the zero moment point method. The zero moment point method takes the central idea of the quasi-static method, but rather than ensuring that the center of mass remains in the support polygon, it ensures that the zero moment point remains inside. The zero moment point, commonly referred to as the ZMP, is a point in space where all moments are equal to zero for the robot. To calculate the zero moment point of the robot, we can simplify the complex model of the whole robot down into a simple inverted pendulum, which can be represented by these two equations shown here. These equations represent the forward and horizontal accelerations of the center of mass of the robot. By rearranging these equations, we can convert them into a strictly proper dynamical system, where the output of the system is a zero moment point. The idea is now to provide a zero moment point trajectory such that when the swing foot finishes taking a step, the zero moment point will now reside in the support polygon of the new support foot. To achieve this, the gate generation method requires future reference of the ZMP trajectory such that the center of mass can start moving prior to the swing foot reaching its final target destination. This is to ensure that once the swing foot has reached its desired position, that the ZMP will now reside in the new support polygon. This can be achieved using something known as a preview controller. If you are unfamiliar with preview control, imagine you are driving a car on a road and a bend is approaching. You as a driver would take this future input and adjust your braking or steering to ensure that you take the bend and do not fly off the edge. This is a similar approach to what a preview controller does. A preview controller takes in the future input references and optimizes the input such that the tracking error is reduced over the whole preview horizon. By interpolating between the footsteps generated by the step planner, a ZMP trajectory can be generated as shown here in blue. Then, by applying preview control, a center of mass trajectory can be generated. Now that we have a center of mass trajectory, as shown here in blue, similar to the quasi-static method, we must generate a swing foot trajectory between each of the steps. Since now we have two trajectories to follow, the inverse kinematics solution will need to solve simultaneously the joint angles that follow both the swing foot trajectory and the center of mass trajectory. The achieved center of mass trajectory after the inverse kinematic solution has been implemented is shown here in the yellow dashed line. Shown here is a visualization of the ZMP gate cycle shown in MATLAB. The ZMP gate generated was also validated within simulation. I will now briefly discuss an optimization routine setup to optimize the gate parameters for both the quasi-static and zero moment point methods. The following diagram illustrates the optimization routine set up between MATLAB and NUBOTS. This allowed hundreds of iterations of varying gate cycles with different gate parameters to be passed to NUBOTS and evaluated. From the optimization routine, combinations of gate parameters were discovered which achieved fast walking speeds. Due to COVID-19 restrictions, the implementation of these walking routines on the real hardware has not been possible. However, we are now looking to implement these walking routines in the coming weeks on the real hardware. All of the MATLAB code utilized to generate the walking routines is open sourced and available on GitHub. Well, thank you for hanging around, and I hope you found some of the results interesting.